here I have a very interesting question, which is, what is the derivative of x to the x with respect to x? And this is going to be introducing a topic that I really much love in calculus called logarithmic differentiation, and we're going to go over what that means. But first of all, shout out to Jackson, who told me that he missed a class on this subject, so this goes out to him. Hope this helps. So, let's try and go about solving this problem, okay? Can we use the power rule? Well, then we get x times x to the x minus 1, but that just becomes x to the x, which would mean it's its own derivative. But later in this video, we're going to show that this is not the case, all right? So instead, we need to do something called logarithmic differentiation. And what is logarithmic differentiation? Well, it's a process of taking a derivative of a function in which you take the natural log, or just the log of that function first, and then you differentiate it with the log. All right, and then you solve for the derivative of y, your function with respect to x, from there. Now this is related to something called implicit differentiation, which is a video that I could make in the future, so let me know, folks. But this is going to be a very interesting topic because behind the idea of logarithmic differentiation and implicit differentiation, you have two very key factors in play. The first being the all-powerful chain rule of derivatives, right, which says that the derivative with respect to some variable of a composite function, f of g of x, is equal to f prime evaluated at the original function g of x multiplied by g prime, all right? And so this is going to be all-powerful chain rule, which we're going to see in play today, but also we're going to see in play the beautiful language and algebra of what we call operators. And there's a video in your that I carded just now, right, should be on your screen, that talks about operators, okay? All right, so first what we're going to do is we're going to note that the derivative with respect to x of the natural log of x is equal to 1 over x. And one way you can look at this argument is using the graph and looking at a visual intuition of the log and seeing the tangent slopes and just estimating the graph at certain points and seeing that its slope is going to decrease even though it goes to a positive infinity. And that's one of the reasons that you can use 1 over x as the reason for being the derivative of ln x. Now, by the chain rule, you can also say that the derivative with respect to x of the log of some function f of x is going to equal, well, first of all, it's going to be 1 over the original function, so f of x. And by the chain rule, you have to multiply the f prime inside, so it's f prime of x, which equals f prime of x over f of x. And by the way, for those of you wondering how you prove the derivative of the log of x equals 1 over x, you can also do it with the definition of the derivative, the limit definition. And that's a really interesting exercise that I encourage you to try on your own. But this quantity here, this ratio of f prime to f, is very important in a lot of mathematics and applications, and it's called the related rate. Okay, so that's something to keep in mind in the future, and it just kind of shows how much the derivative grows compared to the actual function. It shows a change of the derivative with that with respect to the original function. So that's a very interesting quantity, and you can imagine why. All right, so now that we've got some ground rules out of the way, let's go back to the problem of what is the derivative of x to the x. And so I'm going to reproduce the equation right here so that we can get a better look at it. So what we're going to do is we're going to identify what the function that we have is. It's y, right? Y equals x to the x. And why do we do this? Because we want to find, so WTF, want to find dy dx. And this is important to keep track of that while we're doing logarithmic differentiation. So what we're going to do is we're going to apply the operator, which is the log operator. And simply put, if you haven't seen the video on operators that we've made on Josh Academy, what an operator is it's a class of objects that can be applied to both sides of an equation that can essentially input functions and output functions. So when we apply the log operator to both sides of this equation, we get the natural log of y is equal to the natural log of x to the x. And by the power rule of logarithms, you can hop this x out onto the front. So we get equals x log x. Okay? And so I'm going to write that down. ln of x. There you go. So we have ln of y is equal to x ln x. And now we're going to use the derivative operator, which just means take the derivative, but we're going to do it with respect to x. So here's a curly d with a subscript x to define the derivative operator with respect to x. So what do we get? Well, here on the right-hand side, we have 1, or the left-hand side, we have 1 over y. But by the chain rule, we have to multiply by dy dx. And that's what we're trying to find. And now you can see why this is going to be so useful. Okay? And that's going to be equal to the derivative of x ln x, which by the product rule, we have f prime g, which just means ln x here, because f prime of x is just 1, or just x prime is 1. And you add that to g prime f. Well, what's g prime? That's 1 over x. and you multiply that by f, which is x, so that becomes 1. So you have the log of x, all right, and you add 1. So then, by isolating for dy dx, which is what we want to show, we can confirm that dy dx is equal to y times the log of x plus 1, right? And this is interesting because this is equal to x to the x, because that's what y is equal to, times 1 plus log of x. And there you have it. That is the derivative of x to the x, which is interesting because it's not its own derivative. It's sort of like its own derivative and then some. You have to multiply the 1 plus log x term. And in fact, you can see here that if you take this and divide it by the original function x to the x, then of course these cancel, and you get that the related rate is equal to 1 plus log of x. So it's a nice comparison of how those two functions grow. All right, so now we're going to answer a more interesting question. And I'm going to introduce it in a seemingly random way, but consider the function e to the x, all right? So we have e to the power of x. What is the derivative of e to the x? And we're going to use logarithmic differentiation to answer this. So if we set up y equal to e to the power x, okay, then we can take the log operator, all right, big log here, and so we have the natural log of y is equal to, well, the log of e to the x is going to be, by definition, they invert each other and it becomes x, okay? And now I can hit it with a d operator, okay, the derivative operator, with respect to x. And what we do here is, of course, by the chain rule, we say that this derivative here becomes 1 over y multiplied by dy with respect to dx here. And on the right-hand side, since we're differentiating x with respect to x, we get 1. So therefore, isolating for dy dx, we get dy dx is equal to y. But hold on a sec. That means that the derivative with respect to x of e to the power of x is e to the x. And that's an insane fact. And your mind should be blown right now, because we just found a function that is its own derivative. And that's insane. And that's central. This is a central fact of calculus, that e to the x is its own derivative. And so in the future of your calculus journey, you're going to stumble across this important fact many, 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 many times. And you're going to be very grateful to e to the x for having this amazing property. So that's a very interesting idea. The derivative of e to the x is e to the x. But let's generalize this. And what do I mean? So let's take the derivative with respect to x of any base b, that's a constant, to the power of x. Now here, b is greater than 0, because with the negatives you get for any x, it becomes weird on the negative side. And b is not equal to 1, because 1 isn't interesting. 1 to the x is just a horizontal line. We know it's going to be 0. So that's not interesting. So what we're going to do is we're going to do the same thing with logarithmic differentiation. I hope that you can pause the video here and do this on your own already. But what do we get? We get y is, so we set up y equal to b to the x. All right? And what does this mean? Well, of course, as we always do with logarithmic differentiation, we can take the log operator. Now you can take the log base b of this entire situation, but we're not going to do that. We're going to use a natural log because it's a lot faster and there's a reason for that. All right? So you have the log of y is equal to, by properties, we can hop the exponent out. So we get x times the log of b, which is a constant, note. So here we go, b. And now we're going to hit it with a d operator, of course. So the derivative with respect to x. And what we get is we get that 1 over y times dy dx by the chain rule is equal to, well, since ln b is a constant, you can hop that out of the derivative, and the derivative of x is just 1, so you just get the log of b, like this. And so what we get is dy dx is equal to itself and then some, all right? So you get y log of b, like this, which means that the derivative with respect to x of b to the x, so I'm just going to write that like this, b to the power x is equal to b to the x times the additional factor of the log of b. And as you can see right here, the related rate is going to be just simply just a constant, the log of b. So the quotient, the kind of ratio of how fast and how differently those functions grow with respect to each other is a constant. That's an interesting fact. So there you go. If you try and plug in e into this formula, what do you get? You get e to the x times the log of e. Well, we know the log of e is just 1. And there you go. You get e to the x. So that's an interesting fun fact. And now we're going to show an even cooler property of logarithmic differentiation, We've done so many cool things with logarithmic differentiation already, but there's even more you could do. For example, when you learned the power rule, you may have proved it for integer cases, maybe with induction or something else, but how about for all real numbers? How does that work? We have x to the power of n is equal to nx to the n minus 1, the all famous power rule that everybody knows and loves for all n that are real numbers. All right? Except in some cases you have 0 when in backwards cases, but that's okay. There's no way to get 1 over x from this. So, how do you prove this? Well, guess what? We're going to use logarithmic differentiation. So if you have y equal to x to the n, then if you take the log, because we can't use power rule, that'll be circular reasoning. If we take the log operator on both sides, all right, log for big log, so you get the natural log of y is equal to n, which is the exponent, times the log of x, like this. And now, guess what we're going to do? We're going to hit it with the derivative operator, the curly d with respect to x. Now, it doesn't always have to be with respect to x, and in fact, in implicit differentiation, the true meaning of implicit differentiation involves differentiating without specifying which variable you're differentiating with respect to. And that's a bit more abstract, but we're not going to get into that. So anyways, you get 1 over y times by the chain rule, dy dx, and then you get here, well, n's a constant, so it stays on top, and then log of x differentiated is just 1 over x, so you get n over x. So dy dx is equal to n times y, which we can substitute as x to the n, divided by x. And what is x to the n over x? Well, it's x to the n minus 1. So you get nx to the n minus 1, and there you go. We have just proved the power rule for all real n. So you can put down a nice QED, because you deserve it, pat yourself on the back, and there you go. That's another amazing thing you can do using logarithmic differentiation. And there's even more you could do. You could use logarithmic differentiation and the language of operators to prove derivatives of more inverse functions. So for example, let me introduce you to my friend, the W function. All right? And it's called the Lambert W function. So let me see. Lambert W function. Looks like this. I'm going to draw the graph of it real quickly. And there's a reason why it sort of fails the vertical line test here. It's because it has two branches. This is called the complex branch over here, and this is called the principal branch, W0. So don't worry about that specification. Just focus on the idea of what we're going to do with its derivative, okay? So the way it's defined is that the W, a big bold W like this, of x is the inverse function of the function x e to the x. And this has a lot of applications in combinatorics, in solving equations with exponentials, especially in things like physics, electronics, and molecular genetics, and enzyme kinematics. So there's a lot of cool, also biochemical applications. So it is very useful in many fields. You could think of it as a silver bullet, but this is a W function, no matter how you slice it. So that means that another way of saying the inverse of x e to the x is saying x is equal to y e to the y. And you can see how this is not really going to be expressed in terms of elementary functions, your toolkit functions. So how are we going to take the derivative of the Lambert W function? So if we have W of x, that's a horrible W, not bad. Let's see, W of x, all right? We want to find the derivative with respect to x of the Wx. So then we have y is equal to W of x, right? Like this. And that implies, right, using what we can call an operator that's the the product exponential operator, x e to the x, if you will, because they compose each other and they annihilate each other, then x is equal to y e to the y. And of course now you can differentiate this, all right? And so what we're going to get is this. So differentiate it, you get dx, or just derivative with respect to x, if we do this, you get 1 is equal to, and the derivative with respect to x of y e to the y is going to be by the product rule and then chain rule over here, right? We can hop the dy dx like this. We get f prime g, which is just e to the y here, plus g prime f is going to be y e to the y, times dy dx. So then dy dx, remembering that y is the Lambert W function, we get 1 over e to the y plus y e to the y. And we can factor out the e to the y here, like this, and we have 1 plus y. And we can multiply by y on top and bottom to get y over y e to the y times 1 plus y. And now you saw that y e to the y is x, right? It's x. And then 1 plus y and y become the Lambert W function, so you can plug those in yourself. So I hope this was a nice and quick explanation of the usefulness of logarithmic differentiation. Till then.